Assalamu alaikum dear students. I welcome you to 35th lecture of probability and stochastic processes. In last two lectures we have been working with Markov chains. Markov chains represent a special class of stochastic processes. A stochastic process is a collection of random variables. We have been working with collection of random variables for some time, but initially that collection of random variable was just there for us to work with. The relationship between different random variables in that collection was not so explicit as it is in the case of Markov chains or stochastic processes. In a stochastic process, the collection of random variables that we work with have time precedence. There are random variables x1, x2, x3, then x1 is observed at a certain time, x2 is observed at a later time, and x3 is observed at still later time. So the collection has an associated time value. So the value of random variable is observed at a particular time, and the times that these random variables realize their values at have precedence: first time, second time, third time. These times do not have to be equally spaced. If first random variable is observed at time 0 and the second is at time 1 second, the third does not have to be realized at time 2 seconds. It can be realized at 10 seconds, and the next one can be at 11.5 seconds. As long as we can arrange them time-wise, we are fine. Markov chains represent a special subclass of stochastic processes in which the values that the random variables can assume are either finite or possibly countably infinite. This collection of values that these random variables can take is called state space. If the state space is finite, we can represent it with state 0, 1, 2, 3 or any other collection of integers. We can represent these states with other labels, but representing them with 0, 1, 2 type integers is a common method. So we have a collection of random variables, and all the random variables in this collection assume either a finite or countably infinite values. And we have this collection, and this collection is also finite or countably infinite because we are taking these random variables and associating them with discrete instances of time t1, t2, t3. If we have time from 0 to infinity and we only pick discrete instances, we have a possibly countably infinite collection of random variables. So Markov chains represent a subclass of stochastic processes where number of random variables in the collection are either finite or possibly countably infinite, and the values that these random variables attain also belong to a set which has either finite elements or possibly countably infinite elements. In previous two lectures, we worked with a few examples of Markov chains which obey the Markov property, which is that if we know the value of nth random variable, then we don't have to know how this sequence of random variables reached here assuming the specific value of nth random variable. We don't need the history. If we know the value of nth random variable, to find the value of n plus first random variable, we need the value at nth sampling instance and the transition probabilities of this random variable jumping from nth instance to n plus first instance from a certain initial value to the next value. So if we don't need the history to find the probability of n plus first random variable, we only need the value at sampling instance n, then this collection of random variables follows Markov property. This is very useful property and it allows us to simplify the analysis of this type of stochastic processes we call Markov chains. In previous two lectures, we studied the first simple example of Markov chain where there was a machine which had tendency to break down, and if it was working on a certain morning, by next morning it had probability P of breaking down. Once it breaks down, we have different scenarios. One was that it is sent to a repair facility and technicians are so efficient that by next morning the machine is definitely repaired. So probability of machine getting repaired by next morning is 1. Then we looked at a variation of this scenario and we say the machine gets repaired and sent back to the working condition with a probability Q, and it remains in the repair facility with probability 1 minus Q. To make sure that this transition obeys the Markov property, we talked about the technicians losing their memory of previous work. We also discussed other examples, but let's look at another variation of this problem, which was repair of a machine. We extended this problem by introducing a third state. Now we have 0, 1, 2, 3 states, where state 2 represents machine being in working order. State 1 represents machine being repaired in a local facility, which could be at the premises where the machine is installed. And state 0 is a specialized repair facility, could be in the same city, could be in the same country or even abroad. So this is the scenario. If machine is working this morning, it can break down and it will be sent first to the local repair facility. They will have one chance. If they can get it repaired by next morning, they'll send it back. Otherwise, they'll send it to specialized repair facility. And there, technicians will keep on working on it until they fix the problem and send it back. Let's have a look at the state transition diagram for this Markov chain once again. This state transition diagram has 3 states, a few arrows representing possible transitions from initial state to next state, and associated probabilities with these transitions. If the machine is in working condition on some morning, that is, it is in state 2, then by next morning it could be still in working condition, and that is going to happen with probability of 0.9. And with a probability of 0.1, machine will break down and it will be sent to local repair facility, which is represented by state 1. Once there, it will be repaired with a probability of 80% and will be sent back into operation, and with a probability of 20%, it will be sent to a specialized repair facility. Once there, it has a probability of 0.4 of being repaired by next morning and a probability of 0.6 of not getting repaired. If it does not get repaired, the next morning it again has a probability of 40% of getting repaired and probability of 60% of not getting repaired. There are some important properties of this Markov chain that we should look at. First is the observation times. We have said that we are going to observe the state of this machine, whether it is in working condition, it is in local repair facility or in specialized repair facility every morning. So sampling instances or observation times are every morning and they are 24 hours apart. We don't have to have exactly 24 hours apart, but every morning a general window of observation is sufficient. Second characteristic is that none of these states is an absorbing state. The machine does not get trapped on an indefinite basis in any of these states. If it is in working condition, it has a tendency to break down and visit other states. If it is in local repair facility, it is definitely going to move out by the next morning, either back into operation or to specialized repair facility. And if it is in specialized repair facility, it has a positive probability of getting repaired and some positive probability of not getting repaired in one day. But the chance of this never getting repaired is zero, because it will somehow someday repaired and be sent into working condition. So all these states are not absorbing states, and the machine visits from one state to the other to the third one. In the long run, if we want to find the probability of this machine being in a certain state, we can find that from initial distribution and from the matrix of state transition probabilities, which is called transition matrix. Actually, the initial distribution for such a case is not important. Whatever the initial probability distribution, the long-term probability distribution of this machine being in a certain state is fixed as it converges to a specific distribution. We can find that distribution by taking the nth power of transition matrix and seeing if that transition matrix is going to converge or not. In last lecture, we did see that transition matrix for this Markov chain does converge. If we look at the probability distributions at different instances of time, we see that if initial distribution is 0, 0, 1, that is, machine starts its life in state 2, in working condition. Then by next morning, it has 90% probability of being in working condition and 10% probability of being in local repair facility. If you keep on finding the probability distributions at different observation times, you see that eventually it's going to converge to a nice vector of 3 probabilities, which are probability of this machine being in state 0, which is 0.0435, or probability of this machine being in state 1, which is 0.087, or probability of this machine being in state 2, which is 0.8696. The values of this long-term probability distribution depend on the transition probabilities, which are representing how reliable the machine is, how efficient the local technicians are, and how efficient the specialized repair facility technicians are. Based on these transition probabilities, this long-term probability distribution assumes its values, and here we see that in the long run, we have approximately 87% probability that we will find the machine in working condition. If this probability is not good enough for some person, then they can try to change these transition probabilities. They can employ better technicians, they can employ better manufacturing technology to improve the reliability of machine or efficiency of their repair processes. In that case, this probability of long-term finding the machine in working condition may improve to a number closer to 95, 96, or maybe 99%. So Markov chains are important because they enable us to find the long-term behavior of a sequence of random variables which represent a real life situation. In previous lectures, we worked with another example of Markov chain where an average Pakistani Muslim who wants to perform Hajj has to go through some unpredictable situations, and he may or may not succeed in performing Hajj. The internal factors which can influence his intentions are his own financial resources, and external factors are the random draw that has to take place if that average Pakistani goes through the regular channel of Hajj applications. As mentioned in the previous lectures, there are other channels available to people who have resources. These channels allow these people to perform Hajj in the same year that they want to. First of these channels is the channel of tour operators, some well-connected, resourceful people who operate travel agencies, and they get special permission from Ministry of Religious Affairs to take a certain number of Hajis to Saudi Arabia to perform Hajj. They get their special quotas, and against that quota, they seek their clients at their own determined price, and they take these clients to perform Hajj the same year that the client applies. There is another channel available, which is the channel of quota for parliamentarians, governors, chief ministers, prime minister, and the president. This quota for these special privileged people varies from 10 to 50 people. So if you know a parliamentarian and know him well enough, he can put you on his special quota of 10 Hajis, and you can perform Hajj whenever you want. And if you know a chief minister, a prime minister or president, they have a quota of 50 Hajis, and they can put you on a Hajj flight the same year that you want to go. So there are many channels available for Pakistanis to perform Hajj, and the channel available to an average Pakistani is the process of application through different banks. These applications are collected, and if number of applicants is more than the available slots, then a random draw takes place, and the outcome of this random draw determines if a certain Pakistani is going to go to Hajj or not. So this randomness involved in this random draw makes the whole thing unpredictable, and it makes a nice Markov chain. In last lecture, we worked with this Markov chain. Let's continue the analysis of this particular unpredictable behavior of a person who aspires to go to perform Hajj, has to go through some unpredictable states, and eventually he does perform Hajj. Let's have a look at the state transition diagram for this Markov chain. State 0 represents a state where the person has not applied for Hajj. If he has not applied for Hajj, then due to internal factors like his own financial resources, there is a 10% probability that in a certain year he will apply for Hajj, and 90% probability that he will remain in that state where he has yet to apply for it. Once he applies for Hajj, then we have assumed that there is a 60% chance that his name will come up in the random draw, and a 40% chance that his name will not come up in a random draw. If his name does come up, he moves to this state, which represents that he is waiting for the Hajj flight to take him to Saudi Arabia. And while waiting, there is a 99% chance that he will eventually go and perform Hajj, and very small 1% chance that due to sickness or any family reason or any unforeseeable situation, he may not go and fall back to state 1. Once that person has performed Hajj, we assume that he remains in state 3, which represents that the person has performed Hajj. So in later instances of time, when we observe the status of that person, we find that he has performed Hajj, hence he remains in state 3. But the question is, what are those sampling instances? What are those time instances when we observe the state of a person who aspires to go on Hajj? Of course, if we want to see this state, we should observe it after the Hajj has been performed, which is 9th of Zilhajj. So observation at this point could be 10th of Zilhajj, 11th, 12th, 13th, whatever, any date after the official day the Hajj is performed, which is 9th of Zilhajj. Similarly, when should we observe that the person is in state 2 or not. When he is in this state 2, then his application is accepted and he is waiting for his Hajj flight. Then we should observe somebody in this state after the announcement of the results of the draw. And when should we observe somebody in state 1? Once the deadline for applications has passed. All the people who wanted to apply for Hajj, if they have applied, the deadline has passed, we can observe the status of the person a few days after that. And lastly, when should we observe if the person is in state 0? It will be any day after the Hajj has been performed and the deadline for submission of applications has not reached. So the person is here, he is yet to apply for it, and the previous Hajj has been performed. So this state transition diagram with these states and associated observation times gives us a nice model for a real life situation, which is unpredictable situation when a person wants to go to perform Hajj through regular procedure. Let's assume that application deadline is 9th of Shaban and the random draw takes place on 9th of Ramazan. Then our observation times could be 10th of Shaban, which gives us information if a person has applied for Hajj or not, or 10th of Ramazan, which gives us information that if person has been selected to go for Hajj or not. And the last observation time will be 10th of Zilhajj, which tells us if the person has actually performed Hajj or could not go because of some unfortunate situation. Let's find the probability distribution of this Markov chain at a few sampling instances. Assuming that the starting probability is 1, 0, 0, 0, that in the beginning the person has yet to apply for Hajj. If you assume that initial distribution and use the transition matrix obtained from these transition probabilities, we see that the results of different distributions can be found by raising the transition matrix P with appropriate power and multiplying it with initial distribution, which is pi 0, 1, 0, 0, 0. You can see some of these probability distributions on your screen, and you can clearly see that eventually this distribution is going to settle down to a number which is 0 for state 0, 0 for state 1, 0 also for state 2, and 1 for state 3, which means that this distribution is going to converge to a value which represents that eventually the person is going to move to state 3 and then remain in that absorbing state, the state 3, which represents that the person has performed Hajj. We saw this collection of distribution functions in the previous lecture. Here, this is being shown to you just to emphasize the point that because of state 3 being absorbing state, eventually all persons will move to that state, or a randomly selected person, if he keeps on trying through this regular channel, will eventually perform Hajj. And you can see that after 100th try, the probability of him having performed Hajj is more than 99%. Let's have a look at appropriate sampling instances and how they can be used to get a deeper look into this real life situation modeled with the Markov chain. As I told you earlier, a possible collection of observation times are Shaban 10th, Ramazan 10th, and Zilhijj 10th. If we observe the status on Shaban 10th, assuming that 9th of Shaban was the application deadline, we may find that a person has either applied for Hajj or he has not applied for Hajj. If he has applied for Hajj, he has moved to state 1. If he has not, he still is in state 0. Then the next transition comes. If the person has applied for Hajj, there is a 60% probability that his name will be selected and 40% probability that his name will not be selected. But you should see a problem here. When we observe this Markov chain on Ramzan 10th to see if the person has moved from here to here or it has moved from here to here, we see that there is a 10% probability that a person who did not apply for Hajj by 9th of Shaban has moved to state 1. Actually, this is wrong. If a person has not applied for Hajj and he is in state 0, when the time comes for the random draw to take place, he is not allowed to move to this state. He has to wait a complete whole year before the next year applications are solicited. So there is some problem here with this model. This model is too simplistic. So if person is here, he applies for Hajj, fine. If he does not apply for Hajj, he has to wait and the other transitions will not bring him to this state. Similarly, if a person has moved to this state and he is waiting for Hajj flights, then he will move to this state when he performs Hajj, and if you observe on 10th of Zilhajj, he may have moved to this state or has fallen back. But does he fall back to state 1 or state 0? If we assume that he falls back to state 1, we are saying that his application is already in the pipeline. Similarly, when we observe this Markov chain on 10th of Zilhajj, it implies that some of the people have moved from state 0 to 1. That is again wrong. So we have to arrange these transitions in a logical manner which represent the real life situation more appropriately. On your screen, you can see the extended Markov chain which captures this situation where if a person does not apply for Hajj by 9th of Shaban, he has to wait one whole year. I have introduced two new states in this Markov chain, state 4 and 5. Now suppose a person starts at state 0, where he has not applied for Hajj. From here, he'll move to state 1, where he has applied for Hajj, and this move happens with a probability of 0.1. With remaining probability of 0.9, he moves to state 4. He does not remain in state 0 and does not move to state 1 in the next transition. So he moves to state 4, from where it is impossible for him to move to state 1 in the next transition. So 10% is the probability that a person who has not applied for Hajj will apply for it, and 90% is the probability that he will not apply for it. Once he has applied and the random draw takes place, there is a 60% probability that he will move to state 2 and 40% probability that he will move to a newly introduced state 5. So some people have reached stage 2, some people have reached state 5. People in state 2 wait for their Hajj flights, and people in state 5 wait for their chance, which is going to be available next year. Now, from state 2, some people will move to this state 3, which is representing them having performed Hajj, and this happens with 99% probability. But some of them will move to state 0 with 1% probability, where they will be applying for Hajj when the next time comes around. Similarly, all the people who have reached this state 5 will move to state 0 with 1 probability, and then they will wait for next application period where they will apply with certain probability depending upon their financial resources. So this extended Markov chain models this real life situation more accurately, where people wait till the next year before they can apply for Hajj. You can see on your screen the associated transition matrix, and if we use this transition matrix with some initial distribution, which I'm going to assume to be 1 0 0 0 0 0, representing an initial situation where the person has not applied for Hajj, and using this transition matrix we can find probability distribution at different sampling instances. I have found a collection of such distributions and you can see them on your screen. You see that pi 0, the initial distribution is 1 0 0 0 0 0, and pi 1, the observations at next sampling instance is 0, 0.1, 0, 0, 0.9 and 0, which represents that with 10% probability a person has moved to state 1, and with 90% probability he has moved to state 4, and the next transition gives us pi 2, which is also shown on your screen. And you can see that pi 3 is distribution where a person has reached state 3 with a probability of 0.0594. So starting with a person who has not applied for Hajj, there is 6% chance that he will perform Hajj in the same year. There is a 10% chance that he will apply, and then there is a 60% chance that he will be selected, and there is a 99% chance that he will actually go for Hajj. So effectively in 1 year there are 3 transitions from pi 0 to pi 3, and after 3 transitions probability of that person having performed Hajj is almost 6%, and there is a 94% probability that he is back into state 0 waiting for next Hajj application time period. So this Markov chain moves in steps of 3, from this to this to this, again to this, where some people are waiting and some have performed Hajj. If we move ahead by 50 years and see what is the probability distribution of pi 150, 150th sampling time, you see that there is a probability of 0.0468, slightly less than 5%, that person is still in state 0. He has not performed Hajj, and there is a probability of 95.32% that he has performed Hajj. So if this Markov chain is allowed to behave the way it has been modeled here, and a person applies for Hajj again and again, and in 50 years the probability that he has performed Hajj is not 100% but approximately 95%. If you want this probability to improve, reach closer to 1, then you have to change these transition probabilities. You have to increase this probability of 0.6, which represents the percentage of people who get selected in the random draw. You have to change this probability of 0.1, which represents the probability of a person being able to afford to apply for Hajj. If this probability goes up because Hajj expenses go down or economy of the country improves, then probability of somebody not having performed Hajj even in 50 years will go down from this number of 4.68% to perhaps 1% or even less. If you look carefully at this extended Markov chain, you will realize that there is still some timing ambiguity. We introduce these states 4 and 5 to overcome the ambiguity associated with the timing of a person applying for Hajj. We only allow this to happen once in a year. But if you look at state 3, all the arrows come to state 3 from state 3, representing the event that once a person has performed Hajj, he is considered to be a Haji for all sampling instances. So it doesn't matter if we observe this Markov chain on 10th of Shaban, 10th of Ramzan or 10th of Zilhijj. If a person has performed Hajj, he is a Haji and his status will be in state 3. This extended Markov chain assumes that once a person has performed Hajj, he stays there and does not move into this crowd who is trying to find a place in Hajj flights. So a person who has performed Hajj is not allowed to reapply for Hajj. This is again different from the real life situation. Actually, Pakistani government allows a person to wait at least 5 years and then he can reapply for Hajj. Suppose we make this situation simpler and we allow the person to reapply for Hajj immediately after he has performed one. If we assume this to be a situation, then the person who has performed Hajj will not remain in this state, but he will move to this state in the next available opportunity. But all the people who have performed Hajj are not going to move to state 1. Some of them will be happy enough to have performed one Hajj and they will stay in their homes, but other more resourceful and more adventurous people will reapply. So let's assume that if a person has performed Hajj, he is going to reapply with a probability of 5% and he is going to remain in his home happy with one Hajj with a probability of 95%. If you think that this is the correct model, as you see on your screen, representing the situation where a person who has performed Hajj is allowed to reapply, then you are missing the whole point which I introduced here when I introduced state 4 and 5. You see, if a person has performed Hajj and he stays here, we observe it on 10th of Shaban, 10th of Ramzan or 10th of Zilhajj, he is going to stay here. But if an arrow goes from state 3 to state 1, then on every transition, whether it is on 10th of Shaban, 10th of Ramzan or 10th of Zilhajj, he will try to move from state 3 to state 1 with a probability of 0.05. That is not what the real life situation is. This person who has performed Hajj has to wait for a proper time to apply. He can apply only in a certain time period. So he cannot apply on every possible transitions. He has to apply on only accepted transitions. I have worked out the detail of this extension, and on your screen you see an extended Markov chain representing this situation, which models this simplified scenario that if a person has applied for Hajj and there are people who are waiting in state 0, they will apply with probability of 10% and this person is going to apply with a probability of 0.05%. If that person does not apply, he does not remain in state 3. He does not remain in state 3 with 95% probability. He moves to a dummy state 6. So he moves to this state 6 with 95% probability. And when the next transition comes, he moves to state 7 with probability 1. And after next transition, he again moves to state 3. He could have moved to state 0, but I have decided to move him to state 3 to make sure that we mark him as a person who has performed Hajj. So if a person has performed Hajj previously, he will reapply with a probability of 5% and he will move through these states, come back to state 3 where he will get a chance to reapply next year with same probability of 0.05. There are a few observations that we should make before we move forward. If you look carefully at this extended Markov chain, you will realize that there is no absorbing state. Even though a person who has performed Hajj remains in this loop, but none of these states is an absorbing state. The person does not get trapped in any of these states on an indefinite basis. So all of the states are not absorbing states. The other observation is that these state transition probabilities do not change. If we are going to model this real life situation with a Markov chain, then these transition probabilities cannot change. But in real life, these probabilities do change. Suppose for a young person who is not earning much, the probability of him applying for Hajj is small. But a senior person in his middle years who is earning handsomely has a higher probability of applying for Hajj. Similarly, a very healthy person has a very high probability of actually performing Hajj if his name is selected, but a very old and weak person has a lower probability of performing Hajj because he may not be able to go because of sickness. So in real life, these transition probabilities change with time, but we have to assume that they remain the same so that we can model this in a simple Markov chain. Let's talk about long-term probability distribution for this extended Markov chain. This Markov chain has 8 states labeled 0, 1, 2, 3, 4, 5, 6, and 7. If we assume an initial distribution of 1 and then 7 zeros, representing a situation where a person starts in state 0, and then we use the transition matrix to find probability distributions at later sampling instances, we can find the probability distributions of a person being in a certain state at a certain sampling instance. If you form the transition matrix from all these transition probabilities and use that transition matrix along with the initial distribution, you can find probability distribution of this Markov chain at any sampling instance. Since this Markov chain does not have any absorbing state, we can guess that long-term probability distribution will not converge to a value which has a single 1 and many zeros. I have used this 8 by 8 transition matrix along with the initial distribution of 1, 0, 0, 0, 0, 0, 0, 0, and I have found the long-term probability distributions. They do not converge to a value which has a single 1 and multiple zeros, but it does converge and it has a periodic behavior. The thing is, if you look on a long-term basis, a person who starts from this state reaches this state in 3 steps, and once he is there, he can reapply and come back to this state in 3 steps. And if he does not apply, he has to go through again 3 transitions to come back to state 0, from where he can start the application procedure. So we see that this Markov chain has a periodic structure of 3. If you start from here, you will come back here in 3 steps, you will reach here in 3 steps, and from here you will either come back here in 3 steps or go through this process and come back again in 3 steps. So in the long term, if we observe this Markov chain at a sampling instance which is multiple of 3, which represents an instance where a person is found in this state, you see that that converges to a nice vector of 8 values. You see these values on your screen where I have represented it with pi 3k, which implies that this long-term distribution with k approaching infinity represents a stationary value, a value to which the probability distributions converge. If pi 3k is given by this, then pi 3k plus 3, pi 3k plus 6, all the sampling instances which can be divided by 3 are going to give you this distribution, which has a value of 0.2547 for state 0 and 0.7453 for state 3. Remember, this state represents that the person has performed Hajj, and this state represents that the person is waiting to apply for Hajj. So what does this long-term probability distribution tells you? It tells you that an ordinary person who goes through this procedure, if he is observed at sampling instance which is divisible by 3, there is a 25.47% probability that you will find him in state 0. And there is a 74.53% probability that you will find him in state 3. Does this mean that an ordinary Pakistani has a probability of less than 75% of being able to perform Hajj if he keeps on trying? No, it's not the case. These values of 74.5% and 25.4% do not represent the events that in the long run the person who started at state 0 will be in state 0 and the person who started in state 0 will move to state 3. They represent something else. I want you to closely inspect the structure of this Markov chain and try to figure out the meanings of these numbers. What is the meaning of this Markov chain being in state 0 at a sampling instance which is divisible by 3 with a probability of 25.5% and being in state 3 with a probability of 74.5%? I leave it up to you to think about it and figure it out. The next long-term probability distribution is shown on your screen and it is marked pi 3k plus 1. It is a vector of 8 values and 3 values in this vector of 8 values are non-zero. They are 0.0627, 0.2292 and 0.708. Since this is also a long time probability and this represents a sampling instance which is going to give a remainder of 1 if we divide this index. 3k plus 1, 3k plus 4, 3k plus 7 all are going to give you this stationary distribution. And the last long-term probability distribution marked here with pi 3k plus 2 is going to be again a vector of 8 values with 3 non-zero values and 5 zero values. So these 3 long-term probability distributions are assumed by this Markov chain in a rotating manner. If the sampling instance is divisible by 3, you have this probability distribution. If division by 3 gives a remainder of 1, you have the next probability distribution. And if the remainder is 2, you have the last probability distribution. This also shows the periodic structure of this Markov chain. In this collection of long-term probability distributions, we saw that none of the values is 1. All values are between 0 and 1. But there are 3 long-term distributions and they are assumed in a rotating manner, signifying the periodic structure of this Markov chain. And none of these values was 1 because there was no absorbing state. So in today's lecture, we have talked about Markov chains, different real-life situations that can be modeled with Markov chains, and the long-term probability distributions of Markov chains which represent the steady-state long-term probability of this Markov chain being in a certain state. We saw that if we have an absorbing state in the set of states of a Markov chain, then eventually the probability distribution converges to a value which has 1 corresponding to that absorbing state and zeros everywhere else. And if there is no absorbing state, then the values of long-term probabilities lie between 0 and 1. In next lecture, we'll continue to talk about Markov chain. We'll analyze the behavior of these absorbing states and other types of states that we analyze when we are dealing with Markov chains. Till then, I wish you the best. Thank you. Khuda.